Good afternoon, everyone. Today you are here at the 4 o'clock session, the hidden value of remote sensing. Presenter today will be Eric Cole with Woolpert. A couple of housekeeping notes. If you have any questions, please put those in the chat so we can capture them. And if we don't have any time, we will submit those to Eric so he can answer them and get your questions answered. But I'd like to thank everybody again for being here today, and I will hand it over to Eric, and he can introduce himself and start the presentation.
All right, thank you. This is Eric Cole I'm with Woolpert, and I've been with Woolpert for about 15 years now. I'm a program director there and concentrate specifically on our geospatial projects and geospatial clients. So today I'm going to present on the hidden value of remote sensing. We're going to talk a little bit about remote sensing and what it is. And hopefully there will be some time at the end that you guys can ask questions if you have any. And if not, you can send them to me and we'll get answers for them. So what is feature extraction? Basically using different types of data to extract information from that. So simply put, feature extraction is the process of converting different types of data into information. It's the process of feature extraction involves a crucial step called segmentation, and everything that we do is based off of that segmentation. Land cover features are identified, classified, and mapped utilizing remote sensing techniques based on multispectral analysis, patterning, texture, shapes, neighborhood, and proximity analysis. The quality of the segmentation is directly affected by the source data. So higher pixel resolution imagery that you have, the denser point spacing that you have in your LiDAR, the better result you're going to get for feature extraction and remote sensing techniques. The source data comes in various forms. Obviously, you have orthos, you have LiDAR, there's other imagery, color infrared, et cetera. We'll talk about more of that in a little bit later. And this data can be layered or stacked as far as multiple sources of data, or the source data can be fused into one data set for processing. So the advantages of feature extraction, analysis of multiple data sources, as we just mentioned. We get reproducible results, whereas, in the older days, I guess everybody's probably familiar with heads-up digitizing, looking at an ortho image or an image of some sort and trying to decipher and determine what you're looking at, and you're digitizing it and then you attribute it as something. And then another person could do that and you'd get a whole different solution. So with remote sensing, using data and algorithms and computer science, you get a reproducible and repeatable product. It's versatility and adaptability. It's analysis of data pixel by pixel. So we're looking at each pixel of an image and determining what that pixel is or what it belongs to. Analysis of object measures such as shape, size, texture, shadow, context, in association with other features. It's, as I mentioned, a scientific measure of accuracy, and it reduces labor cost and time because the computer is doing the work instead of a person sitting there doing the work. So what makes feature extraction possible? We've got all of the spectral channels of pan, red, green, blue, near infrared, true color, and color infrared images that we use. Any combination of that or all of those to produce data from. The red shows the chlorophyll absorption band of healthy vegetation. Green corresponds to the green reflectance of healthy vegetation. And the blue provides increased penetration of water bodies. And then the color infrared delineates the vegetation and also helps aid us in extraction of the paved surfaces. So also we'll use LiDAR data for remote sensing and feature extraction. So likewise, all the LiDAR data is digital information as well. And LiDAR data implicitly contains abundant three-dimensional and spatial information. Key characteristics include elevation and intensity of each LiDAR point. There's an intensity that's recorded with that. And then patterning can also be derived from the LiDAR data. So for image segmentation, what you can see here in this image, this is showing the region-based approach utilizing region growing techniques applied to a single pixel in order to define an area of similar or spectral textural pixels. So in other words, to simplify that, the process it identifies a pixel within an image and then finds the like pixels around that and continues to grow those pixels into segments. And then you can see the larger segments that have been identified. And as we grow those segments to a point to where the pixels around it are no longer the same, then we have a large segment of pixels and data that we can outline as a common type. And then that's how we begin the attribution and the definition process of extracting features from imagery. LiDAR segmentation. From LiDAR segmentation, we use the point cloud as the key procedure for transforming implicit spatial information to explicit spatial information. So going from what is just a point cloud or a set of points to identifying what those points are. And through that process, there's 4 steps that we follow. So step 1 relates to the different segmentation. Let's see, step 1 is the process of organizing points into an octree structured voxel space. Step 2 is the process of establishing connectivity, so connecting that data together. Step 3 is the process of grouping those points using a best fitting plane. And in this step, we also establish a normal vector, centroid, and boundary for that information. And then step 4 is grouping the co-surface points, for example, points forming a common surface in the process. And then here, I'm just going to show you some examples of, this is kind of examples of what we just talked about. So on the left, you can see an image, and on the right-hand side, you can see the LiDAR data that's been classified. The orange is the ground, and then each of the other colors of LiDAR point is classifying a different plane or a different section of the roof of these buildings. And I'm assuming you guys can see my cursor as I'm moving it around also. And then this is just another view of that same LiDAR data, identifying those same surfaces, but you're looking at it now from a cross section. And then the same information looking at it from an oblique perspective. And then this is a final output of that. Here you have the LiDAR data on the left, the image on the right, and we've outlined using this information, we've created a polygon, and each polygon represents a different aspect of the roof of this house. That same information can be used for change detection. For example, here we're identifying what we might think is a new deck. And we say a new deck with a question mark because eventually you verify that information. But in the process, you use the old imagery and hopefully old LiDAR data. You run processes on that to extract information out of it. You use the new imagery and new LiDAR data, and you run processes on that to extract data. And then you compare those 2 data sets together and you see the hot spots where things have changed. In this instance, we were able to identify where a new deck had been built onto the side of this house. All of this portion right here is new. What we didn't realize is that until we got a better look at the imagery and a better pixel resolution, was that this identified a trash can that was sitting beside the house. So the data, the extraction can be very accurate in identifying differences in old data and new data when you're looking for change detection. These are important, especially for property appraisals when they're looking for changes that have taken place on a person's property that would affect the value of their home and therefore the taxation of it. This is just another view of change detection between data set of 2008 and data set of 2018. And in this instance, we've used parcel data as well. And what we've done is completed a change detection process where we've identified features that have been added, features that have been removed, and features and properties where there's just been change. And then we've color coded each of those parcels based on what has happened there, either something added, removed, or changed. Building outlines is a very common thing that we're producing with using LiDAR and ortho imagery. And I don't know about you guys, but this particular ortho makes my head hurt because it looks like it's a combination of an ortho image and an oblique image, but it really isn't. It's just an ortho. But here you can see the image prior to and then the image after the buildings have been extracted. And then land use, land cover mapping is another area where we're using these techniques. And here you can see an ortho image prior to any extraction that's taken place. And I know a lot of folks would question, well, can you really do land use mapping from this? And the answer is no, not completely, because for one, these automated feature extractions, number one, can't tell the difference between commercial and residential. And then when you get on the commercial side, you can't tell the difference between a mall and a school. So, the land use part is really limited, but you can still identify differences in data and you can generate the polygons. So here would be, where we've actually completed that process, and you can see we've identified the forested area, the fields or tillable areas, what's probably lawns or manicured areas, the roads, the buildings, hydro, etc. And then how do we do that? We incorporate a lot of historical data, parcel mapping, road center lines, land cover, previous impervious surfaces or zoning maps. And in this instance, this is for creating impervious surface mapping. So you can see here the image on the left and road center lines that we may have used on the right. And road center lines are helpful, but definitely, as you guys all know, that if you've ever worked with older road center line data in the past, they very rarely match up to the new orthos that are being produced today, just because of the technology that was used way back when to produce those road center lines. But they do still come in helpful because they can help us identify, that if there's a road center line in the area, that what we've identified as pavement probably is pavement. So this will give you an example using that same ortho imagery when we've extracted the impervious surfaces. So everything that's in white would be considered impervious, and everything that's in green would be considered non-pervious. So this is where water would absorb into the ground. This is where water would run off the ground and into drainage culvert or something that contributes to the stormwater system. It's another example of impervious surface mapping and how we go about it. So here's the ortho image of a large shopping mall. I think this is in Columbus, Ohio. We're using the ortho imagery. We're also using the infrared imagery. And we begin that segmentation process that I talked about earlier, where we're going through and finding like pixels, outlining those like pixels, comparing those to another group of pixels until we determine that all of these are alike enough to create a polygon for that. Same thing here, same thing for this parking area. And then at the end of it, we output all of the line work and the polygons and identify all of the impervious surface features. And as you can see, it actually does capture even the islands that are non-pervious and the parking lots which are pervious. And for the client that we worked on this one, this actually falls in 3 different parcels for them. So now they're able to update their taxation based on impervious surface area for each of the 3 parcels that make up that shopping mall. We also do a lot of wetland mapping using the same processes. So here's an ortho of a wetland area. You've got the river running through here, and there's going to be lots of marshy areas around that. We would use the same segmentation process that we would run through, and then using color infrared imagery as well to help us more clearly define water from vegetation. When you go look at this ortho, there's a lot of areas where you see water, but a lot of areas where you really can't see it either. But when you go to the color infrared, you can clearly see a difference. Water stands out much more than it does on the ortho image itself. And then we can use that information to classify the different wetland types. And basically generating the polygon and the wetland types, a lot of instances would have to come from other information, maybe field checks or something along those lines. But at least we can generate the polygons and make them all different without having to sit down and try to digitize all of that information. Another area where feature extraction and remote sensing is coming in handy, it's becoming a very popular thing, is solar potential. Again, here we'll start with an ortho. So this shows an ortho of various buildings, apartment buildings, and single family residential homes. And we create the polygons for each of those buildings. And then we use surface data that's generated from the LiDAR, and we look at the sun angle from different times of the year. So this is a sun angle and how the sun hits and reflects off of these buildings in February, in April, and in July. And you can see clearly the difference as the sun angle changes and gets higher in the year. The buildings get a lot more sun exposure. And then using that information, we generate a 3D or a solar potential map. And when you look at the roof of the buildings this way within each of those polygons, the brighter the color, in this case yellow, and here almost white, the more sun that area is exposed to over the year. And the areas that are darker in color, the reds, the blues, and the purples, receive less sun throughout the year. And then you could use this information to tell you exactly where you would benefit from putting a solar panel on your home or on your apartment or whatever building it is that you're considering. And then you could see in other instances where you would have a home like this, where maybe solar is not really an option. It's not really going to be a benefit. It would probably cost you more to set up your solar system than the amount of sun that you get to make it worthwhile over a period of a year. And then terrain modeling is another popular thing that we do a lot of with using LiDAR data and imagery. This what you're seeing here on the screen is a ortho image that has been draped over a LiDAR surface to create a 3D terrain model. Some information has already been collected in here. You could see where the water, we've collected polygons for the water and a transmission line that runs across country here. And then this is just another view after we've added in the roads. We have trails and highways, roads, the transmission line again. And then this is a close-up of the downtown area where we've now generated contours, and you can see how the contours overlay with the terrain model of the image actually draped over the LiDAR, and it begins to make a lot more sense of what you're looking at here. So why use remote sensing for these types of products? Because it's reproducible. Again, like I mentioned early on in the process, if you sit down with 3 different people and ask them to digitize the information off of an ortho image and classify what those features are that they digitized, all 3 of them will probably classify it different. There will be some features that they all get to be the same. Then there will be some that they all get a different opinion on. It reduces the field work because, again, using the remote sensing process, once we begin the segmentation and the learning process, we can teach the computer that certain pixels are certain things, and then that identifies those polygons as what they are without us having to go out in the field and check it every time. Reduces the manual edits at the office level, and it simplifies the comparison process, as we mentioned in the change detection earlier on, and it leverages existing data. This isn't Like if someone wanted to do this, you don't have to go get new LiDAR data or new imagery. You can use what you have. You know, the results that you get out of the process will be determined largely on the quality of the data that you put in, but it can still use existing data of any quality and get some kind of a data set return out of it. So that's it. That's all I've got. So I think we've left plenty of time for questions if there are any.
Yeah, right now we have 2 questions that I can see. First one was, what percentage of work do you have to edit the classified impervious surface?
What percentage of, well, I would say that based on our experience, about 95% of what it says is impervious is correct. We probably have to spend a little more time adjusting the line work to make it pretty than we do going back through and double checking what it says is impervious versus not impervious.
Okay, and the other question we have, is there a way to automate polygon building from alike parcels? And digitizing would be laborious.
I'm not sure I understood that.
Yeah, is there a way to automate polygon building from alike parcels?
Let me stop sharing so I can read the question. Is that okay?
Sure.
And then I can read the question from the chat. Let's see. Is there a way to automate polygon building from alike parcels? Okay.
Like in the example with the mall. That was just put in there.
Yeah, I'm still not sure that I fully understand what that question is. I mean, for us, whenever we're automating the polygon building process, the type of parcel, I guess, that it comes from doesn't really affect it because it's just using the imagery. Initially, it's just using the imagery and LiDAR data to generate the polygons, whether it's a polygon that represents a parking lot or a polygon that represents a building. And then it's after the fact that we've generated that information that parcels actually come into effect. Because then we could then classify, we could say we could bring in the parcel data set from a particular client. And if they've attributed their parcels as residential versus commercial, we would then use that commercial versus residential attribute on the parcel data to attribute and identify the type of polygon that we've generated. We could then, if we could then call it commercial or residential. And I don't know if that's answering the question or not. So just not 100% sure on the question.
Okay. Don't see any more questions. It was a comment. Fantastic stuff. So, and at the beginning too, I forgot to mention there will be a poll for the session today. Don't forget to fill that out before you leave.
All right. Well, thank you, guys.
Thank you.